looks like I'm talking to myself, so hopefully some people will join me in a minute. I believe this was the last slide on the narrated PowerPoint. And I just wanted to quickly point out some material on concussions while we've got a picture of the brain and the spinal column there. So concussions are getting a lot of media coverage recently. I think rightly so, to be honest. They are a big problem in certain sports. Gymnastics has a problem, American football has a problem, rugby, they don't even wear helmets in rugby, so clearly they have some issues. And even I think soccer has had some coverage from like heading the ball and other movement patterns that put the brain at risk of concussion. So there's some information that you really have to be aware of. Hopefully you won't be the only person on the field or in the gym at a point where that kind of accident occurs. With luck you'll have an athletic trainer, at least if you're doing like football or basketball or something like that. If you're in the gym, there's never an athletic trainer available in the gym. I've never seen one. So I don't know how come football has to have an athletic trainer available, but the gymnastics facility doesn't have to have one. Remember that concussion does not always equate to a blackout. All right, so the athlete may not pass out or black out for any period of time. The symptoms could be delayed, so they may not show any immediate symptoms at all, which means that if you did not actually see the hit to the skull, then you might not even be aware of the fact that athlete took a hit, whether they hit the head on the floor or whether they were hit by another player. But concussions can result in memory issues, coordination problems, delayed symptoms, maybe things like dizziness or nausea or sleep pattern disturbances, mood swings. Okay. Once you've had one concussion, you're much more prone to receiving a second concussion because that bruising on the brain tissue I don't know if it ever really heals up that way. Post-concussion syndrome can be a problem involving all of these headaches, not being able to pay attention in class. So here I work very closely with the athletic trainers. If I find out that an athlete has a concussion, they're not allowed back in my classroom until the athletic trainer tells me they're okay to come back in. So that means then that we have to work to make up what they're missing, but there's no point in making them more unwell by making them come to class. Okay? And the research indicates that particularly people with multiple concussions then have much more risk of developing things like epilepsy, Alzheimer's, possibly depression. There have been quite a few suicides amongst ex-athletes that have been linked to brain injury that maybe cause depression. Sometimes we like to think that maybe better equipment will alleviate some of the problems. But there's an article up on Blackboard for you that looks at the development of new helmet technology and looking at the mechanics of head injury. and you'll see, read this article because it's really fascinating, that actually better helmets may even make things worse because the athlete thinks, oh yeah, I've got this great new helmet, that's going to protect me, I can go in even harder now, right? So better helmets may not be the answer. You know, maybe it really is rule changes that we have to start thinking about, which I know, you know, purists of these games don't want to change the rules, but we can't continue to see the number of concussions, particularly when we know that having one means you're more likely to have another one, and many of these teenagers are receiving their first concussion before they get to college level sports, right? So, I mean, I got my first concussion in the gym, I was probably 14, right? So, you know, by high school, playing high school football or high school basketball, that's pretty hardcore, right? So we need to be protecting these individuals, and that might involve changing the rules. We'll see, I guess. Okay, so this diagram is of a knee tap reflex, which is also called a monosynaptic reflex or a myotatic reflex. And what you'll see here is that here's the muscle spindle, the blue. Even with my glasses, I can't see this very well. Here's the afferent nerve from the muscle spindle going to the spinal column. And then it synapses directly with the motor neuron back to the quadricep, hence the monosynaptic, right? And that quadricep, remember, if I stretch the quadricep by hitting the knee tendon, then we get the knee kick, which is the reflex of the quadricep contracting in response to the muscle spindle stretch. All right? However, we have a interneuron, so the little green nerve here is an interneuron, which is one of those specialized nerve cells that we talked about last week. And so the afferent nerve also synapses with an interneuron that synapses with the motor nerve to the hamstring. And that is an inhibitory reflex to allow the hamstring to relax, right? So think about it, if the quad was contracting and the hamstring was contracting, we wouldn't see the knee jerk, right? So the spindle is responsible for contracting the quad, but also relaxing or inhibiting the hamstring, okay? For those of you who are athletic training students or physical therapy students, if you go to page 120, there's a breakdown. So when you do a knee tap, a knee reflex test, there are levels of reaction that you're looking for. So that information is available on page 120 for you. This diagram is interesting because it's showing us a form of reflex that is trainable, right? So when we look at sports and we look at very elite athletes and how quick they are to respond to a stimulus and how coordinated their movement patterns are, a lot of that is occurring within the spinal column without input from the brain, all right? So the training of what they call reciprocal innervation plays a large part in these coordinated patterns and these very fast reflexes. So if you think about baseball, pitcher and hitter, or the same in cricket, right? Even though the distance in cricket is further than it is in baseball, that ball moves really fast. The research clearly shows that a striker, a batter, cannot react voluntarily to that ball, right? Because the amount of time from the ball leaving the fingers of the bowler or the pitcher to it reaching the plate or the batsman, the other end of the run, is too fast for a voluntary reaction, all right? So in those kinds of sports, catching, throwing, catching in particular, or hitting, we see a lot of this trained neural pattern, trained reflex. So here what happens is the afferent nerve from the muscle spindle goes to the spinal column, and it synapses with two different interneurons, okay? The interneuron back to the agonist muscle is facilitatory, all right? So it facilitates the contraction of the quadricep. The interneuron that synapses with the motor neuron back to the antagonistic muscle is called an inhibitory interneuron, right? Because it inhibits turning on that antagonistic muscle, all right? So we have a facilitatory interneuron and an inhibitory interneuron, right? And there's some interesting information with regards to training these patterns, particularly with regards to resistance training. Again, we don't want both sides of the joint turning on, but we have to have some contraction in the antagonist muscle to control the weight, right? So I said when we were looking at GTOs that there's some information out there that the GTOs learn, in inverted commas, to turn down their response to a strong muscle contraction, right? And that's part of training. We don't just train the muscles, we don't just train the skeletal system or the cardiorespiratory system. It turns out we're also training the nervous system, okay? Okay, so central nervous system, peripheral nervous system. Okay, hopefully you spent a little bit of time looking at that chart, so you've got those two straight in your head. All right, peripheral nervous system is everything outside of the brain and the spinal column. All right, and the peripheral nervous system carries the information, the command, the signal from the central nervous system to whichever organ it's synapsing with, right? So we have two divisions of the PNS, and that's the autonomic nervous system and the somatic nervous system, sometimes called the sensory somatic system, but I'll show you why I like to try and forget about the sensory bit, because it gets a bit confusing otherwise later on. So autonomic and somatic. So the autonomic nervous system then, the way I remember it, rightly or wrongly, but it helps me, is responsible for automatic responses, right? So things that I'm not consciously controlling, Okay? So my heart rate, my blood pressure, my digestion, my breathing, okay? And there's a very interesting piece in the chapter about yoga and meditation and the fact that studies show that people who are very experienced at yoga and meditation can actually impact their heart rate and their blood pressure, for example. And that's because we can turn down the sympathetic signal to those and slow everything down. But most people aren't conscious, right, of their heart rate and their blood pressure and their digestion. Now, breathing's an interesting one. We'll look more at that when we get to that chapter, because we can consciously control our breath for a short period of time. But if you think about it, like when was the last time you thought, oh, I need to breathe, right? You may not even have had that experience today, right? You just do it, okay? So the peripheral nervous system is divided in two. The autonomic nervous system is divided in two, right? So we have the sympathetic and the parasympathetic systems that sit underneath the autonomic nervous system umbrella, okay? Sympathetic nervous system, sometimes called the fight or flight system, all right? So it is responsible for turning up all those systems and getting us ready to run away from the saber-toothed tiger, or to stand there and punch it on the nose and hope it runs away, right? Which one am I going to do? Yeah, I'm running, right? So fight or flight, okay? So that means that it's got to get me ready to run for my life or fight for my life, right? So I've got to have much more blood flow to my skeletal muscles, so that there's a lot more oxygen and glucose reaching those muscles so I can make ATP to run away, right? That means that my heart rate has to go up and pump more blood to the muscles, right? If my heart rate goes up, my blood pressure goes up. We also see increased glycogenolysis at the liver, so we dump more glucose into the bloodstream, right? And we are able to break down glycogen within the muscle tissue a little bit faster. So all these things are turned on by the sympathetic nervous system, okay? So the sympathetic nervous system then turns on when we're in danger, right? It turns on when we're very, very excited about something. So think about the last time you either had to give a talk in front of the class, or you had to compete, right? Your heart rate doesn't go up when you get on the court or the field and start competing, right? It's already raised before you get out there because you're anticipating the game, right? And for some people that's exciting, for some people that's stressful. Exercise is a stressor. So when we exercise, we turn on the sympathetic nervous system and increase heart rate and blood flow. Okay? If I'm jumping out of an aeroplane, is that thrilling or is that absolutely terrifying? Okay? Psychologically, those two things are different. But physiologically, the response to those two things is exactly the same. Okay? The parasympathetic nervous system is our rest and digest, right? How do I bring myself back to homeostasis? How do I come back to an even keel once I've put the sympathetic nervous system on and I've sent everything haywire physiologically, how do I bring it all back? Right? So the parasympathetic nervous system turns down heart rate, which drops blood pressure, right? It increases blood flow to other organs and to your skin and away from your muscles. Right? It's one of the reasons why you shouldn't eat before you go and exercise, okay? Because we divert blood flow away from the stomach in towards the working muscle tissue. Right? Peristalsis, so that contraction of your stomach and colon and everything, that all is upregulated. Saliva flow is upregulated. Normal bladder function is upregulated. Right? So it helps us get back to rest, physiological rest, if we have been exercising, in our case, or it's responsible for maintaining normal kind of levels of all these functions. Okay, so peripheral, autonomic, parasympathetic, sympathetic, somatic is the other partner to autonomic. All right? And this is why I don't like to call it the sensory somatic nervous system, because the somatic nervous system is also divided into two, the sensory division and the motor division. So I think it gets, at least for my little pea brain, gets a bit confusing. If I see sensory in two places, I start to get them all muddled up, right? So lots of resources just call the opposite to the autonomic, the somatic nervous system, the SNS. So that's not an incorrect way of thinking about it. And then the somatic nervous system then is responsible for responding to external stimuli. So it involves the sensory system, sensory division, that's got all the kinesthetic receptors, right? Our Golgi tendon organs, our muscle spindles, our joint receptors, all the different kinds of receptors in our skin, taste receptors, right? Vestibular system, all those sensory organs that we have many, many of, all send information via the sensory division to the central nervous system. Right? And then the central nervous system sends information back what to do in response to that environment, to that stimulus, comes back via the motor division. Right? Questions? Questions? We might do that. Let's do that one as well. Okay, no questions so far? All right. Okay then, so one of the things that we're interested in when we are working out, whether we're working out for health or we're working out to compete, right, is this idea of fatigue. Like, how do I avoid fatigue? How do I recover from fatigue? What is making me fatigued, right? Where is that fatigue occurring within the system, okay? So it's quite complicated when we look at the nervous system to think about where is the fatigue happening, particularly when we look at the central nervous system. All right? In the periphery, when we look at the peripheral nervous system, fatigue is a little bit easier to pinpoint, I guess is the way to say it. All right? Because we've got to transmit the signal, the motor signal, the action potential along the sarcolemma, down the T-radial to release the calcium, right? So we go back to our muscle contraction idea. So peripheral fatigue could be that the sarcolemma doesn't have enough potassium to transmit the signal appropriately, right? Or we could get down to the sarcoplasmic reticulum and we're short on calcium, right? So peripheral fatigue is quite easy to kind of get an idea about. We've got too many hydrogen ions in the muscle cell, and so glycolysis slows down and ATP availability is decreased, right? So this idea of peripheral fatigue is quite, I think, quite logical to understand. Central fatigue, though, when we look at the nervous system, is so much more abstract, okay? And we don't totally understand where fatigue occurs within the nervous system. We know that initial stimulation of a motor impulse can be affected by my attention span, by my motivation, all right, by my drive to succeed at the skill, right? There's some information that there might be some fatigue occurring in that motor output. So that signal has to be sent from the brain down the motor nerve, down the spinal column, to the motor nerve. The motor nerve has to be myelinated. What if the myelination is defunct somehow, right? If you have MS, multiple sclerosis, when you watch people with multiple sclerosis, before they get too far advanced, their movement patterns start to become very uncoordinated. It's quite weird. It's not that they can't walk, at least to begin with, but the walking pattern becomes very uncoordinated. That's because one of the problems in multiple sclerosis is the myelin sheath gets degraded, and that slows the signal to the muscle from the brain or the spinal column. Okay? So, again, there could be something with that. There could be something occurring at the synapse, right? So maybe there isn't enough acetylcholine available to transmit that signal across to the muscle. We don't quite understand what's going on. We do, but except that we know that we do see fatigue that is not related to things we can directly measure in the periphery. Right? Physiological fatigue, not fatigue, oh, I'm tired today, fatigue, right? Fatigue means a decrease in power output. Right? So, we see a decrease in power output that has nothing to do with the muscles, with ATP, with substrate availability, right? Those are all fine. And yet, sometimes power output is down. Right? So we know that there's something going on centrally, we just don't have the whole picture of what it is yet. Okay, this is one of my favorite diagrams. I think this really helps. Uh-oh, hold on, I need to change these batteries. You guys aren't going to be able to hear me. Hang on. Cool. put it. Let's hope the batteries that Marshall gave me are ready to go and not defunct. There we go, perfect. Okay. All right, so great. This is a great diagram. All right, so we're going to look at what constitutes a motor unit. All right. So a motor unit contains a motor nerve, a motor neuron, and the muscle fibers that that motor neuron synapses with. All right. So any of the fibers that that neuron stimulates are part of that motor unit. Okay. So here in this diagram we have two motor units. The one on the left has 4 muscle cells, fibers that it's synapsing with. It would be synapsing with hundreds. So this is a much, much simplified picture, right? And the unit on the right is synapsing with 3. Okay? So when we look at this, the alpha motor neuron has relatively short dendrites. Right? Remember that the cell body is located within the spinal column. And then a very long axon, dependent is only one motor nerve, right? One axon all the way down to the muscle. So it might be quite a short axon if it's stimulating muscles in your back, or it could be a very long axon if it's stimulating muscles in your toes. Okay. So the number of muscle fibers that it synapses with, that it talks to, right, depends on how much control is needed. All right. So if it's fine control, like in my eye, then the muscles that move my eyes might only synapse with 10 muscle cells. Okay. When I look at my calf, it doesn't have to do anything particularly elegant, right? It just has to contract like bilio. So there, a motor unit might have 1,000 muscle cells, muscle fibers. Right? On average, a motor unit has about 100, but I really think that that number is a little misleading when you can go from 10 to 1,000. Right? I think the 100 average is a bit misleading personally. Okay? So, we have 3 types of motor units. All right? One is smaller, the cell body is smaller. All right? And it's an S unit, so it's S for slow, and it synapses with type 1 muscle fibers. I think I'm going to write this down. Let me do this on the whiteboard. Where are we? We've got a few minutes yet. Okay. So, the motor unit can be S, all right, for slow, and that is going to and that is going to synapse with type 1s. Okay. The second one is called an FFR, which is fast fatigue resistant. Okay. So what kind of muscle fibers do you think FFRs synapse with? Fast fatigue resistant. What are our other two types of muscle fibers that we know of for sure in humans? Natalie. So it's really important to understand that the nerve cell dictates which muscle fibers it's attached to, right? So a motor unit only has one type of muscle fiber. Okay? If the motor unit is an S, then all these fibers that motor nerve synapses with are type 1s. If the motor unit is an FFR, then all the muscle fibers are type 2A. If the motor unit is an FF, all the muscle cells are type 2X. So, we need to understand how the signal gets from the central nervous system to the muscle. Right? So, remember we said that muscle tissue is excitable. It's able to carry an electrical signal. Right? So, we have a situation where the signal, or the impulse, or the technical term is the action potential, is an electrical stimulus that's being passed down the nerve that then stimulates that muscle fiber to contract. Right? So when we look at the movement of this electrical signal, it works in a similar way to the electrical wiring in your house. Right? We have resting membrane potential. That means that that nerve is not carrying a signal at that time. Right? Resting membrane potential in a motor nerve is about minus 70 millivolts. And we have to change that resting membrane potential. So the potential across the membrane of the nerve from the outside to the inside. Right? Remember that ions carry a charge, so there are all these ions floating around that have negative or positive charges. We have to shift that balance from the outside and the inside from minus 70 to something else in order for the signal to continue along. Right? So a term you'll see a lot is threshold. Okay. So what we have to do is change the charge between the outside and the inside of the nerve cell to a point that reaches a threshold so that the cell can depolarize. Right? Depolarization means that there are gateways called channels, and we want, for a depolarization to occur, we want the sodium gateway to open up and allow sodium to enter the cell from the outside of the cell. Sodium is a positive ion. So by opening up the gate and letting more positive ions in, we change the ratio, right? What we call the potential across the membrane. Right? So depolarization is pretty straightforward. The thing is, once I've depolarized it, if it wants to carry another signal, it has to go back to rest. Right? So the fascinating thing when you look at a nerve cell is it can only carry a signal from rest. Right? It goes rest, depolarization, then we have to have a period of repolarization back to rest before the next signal can be conducted. When we see repolarization occurring, another gateway opens up called the potassium gate, and it allows potassium ions to leave the nerve cell, and we get back to our minus 70 millivolts. So it sounds hugely complicated, and it is, but it occurs in the merest flash, right? Faster than we can even begin to imagine. Just a few milliseconds for rest, depolarization, repolarization, back to rest. A few milliseconds. So this is where we will start on Wednesday. And we'll review that idea with some diagrams. Help us out a bit. Because it's always easier with diagrams. Questions? Okay. I have office hours this afternoon. If you think of something you would like to review, you can jump on into office hours or send me a discussion board question, and then I can answer it and everybody can get the benefit of the answer. All right?